Alright, so we're continuing from mechanics, chapter 4, 4.2, limit of friction. Right, limit of friction. Okay, so we've seen that when an object is in limiting equilibrium or in the point of slipping, friction takes the maximum value. So when an object is moving, friction will remain at the limiting value. Okay, what does that mean? It means that depending on whether the object is slipping down a slope, for example, or is being pushed up the slope, so therefore we have a slope with an angle, and it's on the point of slipping, meaning that the resultant force is going to go downwards. Okay, friction is going to oppose that. All right, friction will oppose that. But if we have our resultant force pushing upwards, so it's limiting equilibrium, same as before, except it's going to be moving upwards, right? So I'm pushing it up the slope and at a limiting equilibrium, so it's just about to move. Okay. Alright, so that means friction will oppose that motion and go downwards. Alright, it's going to change depending on the type of question that we have, and we have to make an assumption. Okay. At this limiting equilibrium, our frictional force is going to be equal to the coefficient of friction multiplied by the normal contact force, known as R. I like to write it as frictional force is equal to coefficient of friction times the normal contact force. Alright. Now, when an object is moving or about to start moving, we mark the friction as equal to this. Alright. So, we can do some questions based on this. Okay. So we have a curling player tries to slide a curling stone of mass 20 kgs, 20 kg stone along a horizontal ice rink to stop on top of a target that is 46 meters away from where it was released. The coefficient of friction between the ice and the stone is 0.5, so that's coefficient of friction, 0.05 I mean. Right? The player releases a stone with a speed of 6.5 meters, so its initial velocity basically is equal to 6.5 meters per second. Alright, find how far from the target it stops. Okay. Also said that the distance was 46 meters away where it is released. Alright, so we have all of this information. We have to find how far from the target it stops. So, doing the force diagram, alright, we have, I don't really have to take that into account. Okay, so the curling stone will have gravity pushing down on it, alright, that's the force of gravity, alright, from its weight, which is m, which is 20 kgs, times gravity, which is 10, in mechanics is 10 meters per second squared. Okay. Then we have our normal contact force pushing upwards. Alright. In this case, these two are equal to each other. Okay. Why are they equal to each other? Well, they're equal to each other because there's no acceleration in the vertical direction. Alright. There's no acceleration up or down. Okay. No resultant force. Alright. So the direction of motion is to the right, okay, and our acceleration is to the right for now, just after it's been thrown, but then it starts to decelerate actually, okay, it starts to decelerate. Why? Because all we have is our friction. Alright, so we have to find where about it stops. Okay, so to find how far from this target it stops, we'll solve that now. So thinking about it, Remember, normal contact force, if we're solving for friction, we have to find normal contact force. So normal contact force is going to be equal to the force in the opposite direction. So that would be 200 newtons, which comes from gravity, alright, gravitational force. Then to find frictional force, we just multiply the coefficient of friction multiplied by normal contact force, which is 0.05 times 200. Okay, that should give us, if I work it out, should be 5 times 200, that's 1000, 2 dots less, so it should be 10 newtons, I think. Alright, so if I check 5,000, 100, yeah, 10 newtons. Okay, then I can solve for my acceleration. Alright, so my resultant force in this case would only be equal, okay, to this. So that would be 10 newtons is my resultant force. Why? Because we have frictional force, right, backwards, in this case negative, alright, negative, but there's no applied force here. So really, it's applied force, which is none, minus frictional force. So we'll get applied force is 0, frictional force is 10 newtons. Alright, that means our resultant is negative 10, and we know that the resultant force is always made up of mass times acceleration, which is, if we check our mass, 20 kgs, so it's 20 times a, and 20 times a equals negative 10. Alright, dividing, we'll get negative half, or negative 0.5 meters per second squared. Okay, now using this acceleration, we can then have, remember we need at least 3 different forms of information when we're doing our Suvat equations. Alright, in this case, this s is not the distance we're moving, but rather the distance to the target, and we have to find the distance, alright, that we move, okay, that this curling stone moves, alright, and then minus it, okay, from this. So what we'll do is we'll take our initial, which is 6.5 meters per second, we have our acceleration, and then something else we have, alright, I'll get to it now. So SU, okay, VAT. So S is what we're trying to solve for. U we know 6.5 meters per second. V is what? Well, we know it's going to stop, so that's going to be 0. Okay, that's our third one, meters per second. And acceleration is negative 0.5 meters per second squared. Okay, T we don't need. What equation can we use here? Well, if you look to Suvat equations, you'll find that the best equation to use is v squared equals u squared plus 2as. Alright, so 0 squared equals 6.5 squared plus 2 times negative 0.5 times s. Alright, if you solve for this, okay, meaning you move 6.5 squared to the other side, that's going to equal to negative s basically. S is going to equal to 6.5 squared, which then equals to 42.25 meters. Alright. Okay, so the distance between where the target is and the actual distance we moved would be 46, which we found at the beginning, minus 42.25, and that's going to equal to 3.75 meters. Okay, that was the distance from the target. Okay. Next, I think they asked, in a game of curling, there are sweepers who sweep the ice to polish it and reduce the coefficient of friction. Assuming they lower the coefficient equally along the entire path, find the reduced coefficient of friction required to get the stone to land on the target. Alright, so it has to land on the target and not miss it by 3.75 meters. So what we need to do is find that acceleration that you would needed. So SUVAT, we want this to equal 46 meters. It needs to be equal. We know that the initial is 6.5. We know the final is 0. Okay, meters per second in meters. All right. Acceleration is what we need to solve for this time round. I have to know what force basically would need to be applied, because then force is related to our frictional force. All right. Remember, our frictional force was equal to our resultant force in this case, or the negative version of the resultant force. Then we can find our acceleration. All right, that is necessary. Okay, so we need to find our coefficient of friction then. So first we're going to find acceleration, then we're going to find the frictional force, and then we're going to find the coefficient of friction. So what we'll start with is the same equation as before. V squared equals U squared plus 2AS. That's 0. 6.5 squared plus 2. A we don't know. S we need it to be 46. Alright, that's negative 6.5 squared. I think that's equal to 42.25. Alright, negative. And 90. Is that 92? Yeah. Alright. Then acceleration is going to end up equaling to negative 0.459. So 3 significant figures. Okay, meters per second squared. That's our acceleration that we need, okay, to reach that point. Basically, we need to slow down less, because before it was 0.5, that we're decelerating at a higher rate. Okay, not decelerating at a higher rate, but rather we're slowing down at a higher rate. Okay, our velocity was decreasing at a higher rate. Here, it's at a lower rate, which means we'll travel a bit further, which is what we wanted. We're going to travel an extra 3.75 meters. So now we need to find our resultant force. That's mass times acceleration. All right. Okay. So resultant force will be this, and then our other frictional force will be equal to Fg, remember, which is equal to, let's remember what it was equal to. It was 20 times G. Okay. Sorry, not frictional force. My normal contact force. Okay, so that's 300. And so frictional force is equal to coefficient of friction multiplied by 300, because remember, coefficient of friction times normal force. Alright, that's a normal force. Then I have coefficient of friction times 300 is then equal to, actually I should move this to the right side, is then equal to, okay, our resultant force. Alright, and remember, if I write this out nicely, in an equation it would be resultant force is equal to F applied, remember that's 0, minus frictional force. Okay, so resultant force is 0 minus frictional force, which is what should I say, coefficient of friction 300. Alright, so we have that, and resultant force we found already was 20 minus 0.459, okay, which is equal to negative coefficient of friction 300. Alright, so solving for this, you can then divide by 300 or negative 300, okay, and you get the coefficient of friction is 20 times 0.459 over negative 300. Your final answer should be 0.0459. Why is it the same? Because it's almost the same, because as you know, this 300 was made up of the 20 and the 10. Alright, that's 20 negative 0.9. Alright, so this 20 should cancel, and so I'm just dividing by negative 10. Okay, and by dividing by 10, I move the decimal place. Okay, so I end up with almost the same answer, just moved by one decimal place. Okay, so that's my coefficient of friction and my final answer. Okay, so that's how you would solve for a question that has frictional force and coefficient of friction involved. Okay, then we have one more question, and then we'll stop with mechanics. So a woman drags a box of mass 20 kgs up a rough slope. Alright, so we have a rough slope. Rough slope, remember? Rough slope means there's friction. 10 degrees. Alright. It's 20 kg box. Okay. Coefficient of friction is 0.45. Right. Woman pulls the box using a rope held at an angle of 20 degrees above the slope. 20 degrees above the slope means this. So if this is the slope that's parallel to the slope, 20 degrees above would be like that. Okay. And it says 120 newtons is the force being pulled. Okay. Find whether the force is large enough to create motion, and if it is, find the acceleration. Alright, the other forces acting on the box. Remember there's Fg going straight down, but now I'm going to find the components of Fg. Alright, the components, Fg perpendicular, which is equal to Fg cos 10 degrees. Alright, we have Fg parallel, which is equal to Fg sine 10 degrees. We also have frictional force, alright, which is just coefficient of friction times normal contact force. And then we have the normal contact force, which is opposing gravity, alright. The interesting part of this question, though, is that the normal contact force is being helped by this upwards force, alright. So because it's being helped by the upwards force, this normal contact force is less. Okay, so now normal contact force would be equal to basically Fg perpendicular would be equal to normal contact force plus 120, in this case sine, because sine is opposite. Okay, sine is the upwards force there. Sine 20 degrees. Alright. And then we would solve for this and solve for this, and then we could solve for our normal contact force. Alright, so before anything else, we need to look at what is now in the slope direction. So this direction here, okay, this direction and this direction. So solving for that one, we should get move this, yeah, should get, let's look. Okay, we have 120 that's pushing forward. It says find whether the force is large enough to create motion. Okay, so the force we're talking about is the force up the slope. That would be 120 cos 20 degrees. Alright, so my resultant would be 120 cos 20 degrees minus the other forces. That's frictional force minus Fg parallel. Alright, so that's our two equations. This one is in the perpendicular direction, and this one is in the parallel direction. Alright, or with a slope. Solving for the first equation, perpendicular direction, we have Fg perpendicular is, Fg first of all is equal to, weight is 20, and then gravity is 10, so mg That's 200. All right. 200. Okay. I just want to see something quickly. I think I made a mistake here somewhere. I did. I made a mistake here when I multiplied. Whoops, it's 200. Sorry about that. 200 again. 200 and 200. I don't know how that happened. Right. Okay, sorry about that. Might be confused in the previous question. Right, I meant 200, not 300. So mg, that's 200. I mean fg. So then we have, all right, fg perpendicular is going to be equal to 200, which is our fg. And that's cos 20 degrees. All right. So that's this part here. Then we're going to have 200 cos 20 degrees equal to Fn. Fn is, we'll solve it for it now, plus 120 sine 20 degrees. All right, you guys can solve for this and then minus. Okay, move this to the other side and minus. You should get that Fn is equal to 156 newtons. All right. In the next section, we do this the parallel. All right. Since we've now solved for Fn, we can use our coefficient of friction, which I said was 0.45. Okay. 0.45 is coefficient of friction. Okay. So that means the frictional force equal to coefficient of friction times normal contact force, which is 0.45 times 156. All right. So using our parallel, we have resultant force. Okay, maybe I should just bring it down so you can see it. All right. That there. Okay. So subbing everything in, we get resultant is 120 cos 20 degrees. That's our applied force minus frictional force. Okay. So 0.45 156 minus FG parallel, which we knew is 200. Okay, that's FG, and then sine 10 degrees. All right, solving for this, you should end up getting, okay, remember FR is equal MA, okay, M being 20 kgs. So I rub this out, 20 times A, and I end up finding, after solving for this and dividing by 20, okay, on both sides, we get that A is equal to 0.393 meters per second squared. All right, what does that mean? It means that we're moving, okay? And the original question was, find whether the force is large enough to create motion, all right? So the force is large enough to create motion because there's acceleration, okay? And then it says find the acceleration, which we just did, okay? So 2 birds, 1 stone. All right, so now I'm going to go into physics because that's the end of limiting friction. Okay. The next section we're going to go to is change of direction of friction. We can do that next time. All right. So in physics, we have gravitational potential to kinetic energy transformations. So whenever we have gravitational potential energy, you guys remember? Gravitational potential energy and kinetic energy. Remember I mentioned that work done is made up of these two. Alright? So your work done will be made up of gravitational potential energy and kinetic energy. What's really happening here is that gravitational potential energy is changing to kinetic energy, or kinetic energy is changing to gravitational potential energy. And I'll explain why. So you know gravitational potential energy is equal to mass times gravity times change in height. Okay? Kinetic energy is equal to half times mass times velocity squared. What does that mean? It means kinetic energy only happens when there's a velocity. It means we're moving. Okay? And gravitational potential energy only takes place when we're at a specific height. Okay? There's a potential for energy use by gravity. Okay? So gravity can do work on an object. Alright. So now, for example, if I had a slope like this, alright, first we have gravitational potential energy is equal to 0, okay, because we're on the floor, right? There's no height. But Ke, or kinetic energy, is at its max, alright? Okay, not max necessarily, but it's the only form of energy that we have, alright, that's happening as we're moving forward. And as we move up, our kinetic energy is changing over to gravitational potential energy. Alright, so our Ke will become smaller. So why? Because our velocity is decreasing as we go up, because we're slowing down from the hill. Alright, but our height is increasing, the gravitational potential energy increases. Okay, at the top of the hill, gravitational potential energy will be at its max. Alright, and at one singular point here, kinetic energy will basically be 0 because you won't be moving for a split second before we go down. Alright, and then as soon as we go down, alright, gravitational potential energy all gets transferred back over to kinetic energy and we speed up. Alright, and at the bottom, everything is kinetic energy. Alright, and gravitational potential energy becomes 0. Okay, so that's how it works. Alright, hope you guys understood. Okay, so then we can do a question based on this. So they say a sphere is pulled to the side that it is, okay, draw this. Alright. Okay, make that. Alright. It's basically swinging in this direction. At its lowest point, that's its highest velocity. It's basically our highest Ke, highest kinetic energy. At the highest point here, that'll be our greatest gravitational potential energy. So between these two, the height difference is 0.15 meters. Okay, so they want us to find this velocity at the bottom. All right, basically at its fastest speed. Okay, where the kinetic energy is its highest. Well, at the lowest point, the gravitational potential energy is 0. Okay, so that means all of the gravitational potential energies change to kinetic energy here. All right, at the lowest point in the swing. So if I calculate gravitational potential energy, it's going to be mass. Okay, so they give the mass as 5 kgs. So it's going to be 5 times 9.81. Remember in this book it's 9.81 for physics, times height. The height is 0.15. That gives us 7.36 joules. Okay, and the kinetic energy, all right, at the bottom is going to be equal to gravitational potential energy because all of the gravitational potential energies change to kinetic energy. So that means 7.36 joules is going to equal to half times mass, which is 5 kgs, times velocity squared. Okay, so we can find our velocity that way. Okay, so this is equal to 2.5, and if I divide 7.36 by 2.5, okay, and I square root both sides, alright, I'm going to get that my velocity is equal to 1.7 meters per second. So that's my highest velocity. Okay, so you see how it's all changed over. I can even solve for my velocity, and vice versa, by the way. So if we knew the velocity at the lowest point and they didn't give us the height difference, we can then solve for the height. Okay. Then we go over efficiency. All right. Okay, so efficiency is equal to useful. Okay. In this case, useful energy. Okay. Useful output energy. Okay, the energy that is output in the system that's useful over the total input energy, so the amount of energy we input at the beginning. All right. And generally speaking, we want this in terms of a percentage, so we multiply by 100. Okay, so percentage efficiency. For example, in an engine, we can have majority of the energy. Okay, so we have chemical energy, that's our gasoline or petrol as we know it. Chemical energy, and that changes over into our kinetic energy, right? That we move with, okay? But only a small amount is changed kinetic energy. The rest is actually lost as heat. All right. So as an example, okay, they have a question where we need to figure out the efficiency. All right. So they have a dam. An example question. They have a dam. This is our outlet of the dam. All right. And from the dam, let me just, okay, that's fine. Just wanted to get rid of that little thing. Let's go F. From the outlet of the dam, we have a difference in height of 20 meters. Okay, and the velocity that this water is moving at, just outside of the outlet, is equal to 16 meters per second. Right, moving out of the outlet. Okay, so we can calculate kinetic energy essentially. So if we first take the kinetic energy, all right, kinetic energy just outside the outlet, all right, we want to actually find in this question the amount of GPE that's equal to our kinetic energy. All right. In this case, not all of the gravitational potential energy gets transformed into kinetic energy. Why? Because some of it is lost through friction, etc. And so there's certain processes that take place where other energy causes losses, such as heat, etc. All right. There's many different reasons why we'd lose energy, but for the most part, there's no lost energy per se. It's just been transformed into another form of energy, and we'll go over that just now. Essentially, we talk about the principle of conservation of energy. Okay, I can go over that now. So conservation of energy basically means that no energy is ever lost. Okay, energy cannot be created nor destroyed, and it can only be transformed from one form of energy into another. Okay, so in this case, we only talk about gravitational potential energy and kinetic energy. And so we need to find what our kinetic energy is, okay? And we don't know what the mass is, but it doesn't matter. We don't need to know the mass of all of the water. We can just take, for example, a liter of water, all right? A liter of water in terms of mass will equal a kg. So we say 1 kg, velocity is 16 meters per second squared. All right, so our kinetic energy would be 128 joules. Okay, outside the outlet. That's our output. Okay, this is the useful output. Okay, energy. Then the initial total, okay, so total input energy is going to be our gravitational potential energy, which is equal to mass, which we said was 1 liter, so 1 times mass times gravity times height, so 9.81 times the height, which was 20 meters. All right, we gave it as 20 meters up here. That's going to equal to, all right, 196 joules. So you can see already that there's a difference here. Okay, they're not equal to each other. Therefore, there was some energy turned into a different form of energy. Okay, didn't go straight from gravitational into kinetic. Okay, so we have gravitational. All right, that's our total over our 128 of kinetic energy, and that's going to be times 100. So yeah, useful output. Okay, that's our kinetic energy output, and our input of gravitational potential energy. That should give us about 65%, all right, efficiency. Okay, but in the question they ask how much energy is lost, or the percentage energy lost. Okay, so the percentage energy lost you can see is 35, or we could have taken, if we hadn't solved already, we could have taken 196 minus 128. That would have equal to 68 joules. So 68 joules was lost, and therefore 68 over 196 times 100 equal to 35%. Okay, energy basically lost. Not lost, but turned into a different form of energy that we didn't want. Okay, it's not useful energy. All right, so stop there, and we'll continue on from power next time. I hope you guys understood the lesson, and have a good evening.